Just get my screen set up, 1 second. Sorry guys, just 1 second. Okay, hopefully.
Practices.
Yeah, we did, but then I blew it. Hopefully everyone can see my
so you're in presenter mode for us right here, so I can see what's coming next as well.
Okay.
Display settings.
1 second. Is that still in presenter mode?
It is, yeah.
Just 1 second.
I think if you just click display settings on the top panel, then you can quickly change it.
Did that fix it?
Yes.
That's fine now, yeah. Perfect.
Okay, thank you, Kristen. And sorry I blew that at the start. We did practice it, but then I got it wrong. Thank you everyone for listening in. As Kristen said, today's talk is going to be about some work that I've been undertaking over a couple of years up in the Cook Islands, but most of the experiments were a couple of years ago now, at a location called Muri Lagoon. And I have talked about some of this work previously at a Engineers Australia New South Wales COPEP talk, so it's probably going to be fairly similar today. So if you did hear me talk about it previously, then you probably don't need to be here again today. But there will be a few things, bits and pieces different as well. So the location that I'm going to be talking about is the left-hand half of this slide on the screen here at the moment. As I said, it's called Muri Lagoon. It's about a couple of kilometres of coastline on the island of Rarotonga. It's a really important site for a whole bunch of reasons. I'll just tell you some of those as a bit of background. It's probably one of the crown jewels in the tourism aspect of the Cook Islands, in that there's quite a lot of hotels based on the coastline of the lagoon itself. So it has a big economic contribution to the island. But looking a little bit deeper than that, it's also the only location, I think, in all of the Cook Islands, but certainly in Rarotonga, where there's salt marsh areas around the foreshore. And that's because of the geomorphology of the islands, the Motu, around this part of the coast. There's also a few marae or sacred sites, traditional sacred sites around the foreshore of both the Motu Tapu, the main Motu there at the north, and also on the northern side of the Reef Passage. So, and there's a lot of history around, a lot of Polynesian history linked with this particular location. So there's a lot of cultural significance, a lot of economic significance, and it's certainly got a lot of social significance to local people that own properties around this part of the island as well. So it's a really important site. For me, it's one of these locations that you probably get to work only once in a career, and it's one of these sites where you just keep learning more and more and more interesting things about the location, but about coastal science and coastal engineering. The more you look at it, the more you learn. So it's a really rich site from that perspective as well. I'll just acknowledge that the work I'm presenting was a part of a bigger project called the Metavai-Kitavai project with other consultants from WRL. A lot of this work was undertaken with Chris Drummond, and I know he's listening in, so I just wanted to acknowledge his contribution, especially to some of the hard yards in the field work. Okay, the Cook Islands out in sort of the central Pacific, it's over between French Polynesia and Samoa is probably the best way to talk about the location. It's about a 5 to 7 hour flight from Sydney. The Cook Islands, for those who don't know, is split into two groups. A southern group of islands, it's shown in the left-hand part of this slide here. The southern group of islands, the northern group of islands, I mean, is mostly atolls, closer to the equator, and then the southern group of islands is a mix of partial atolls, ex-volcanic islands, that kind of thing, and a few Makatei or raised coral islands as well. Rarotonga is the main island of the Cooks and one of the most southern, as you can see in that picture there. It's about, to give you some perspective on the size of the island, it's about a 40-45 minute drive around the coast of the island if you want to do a whole lap. Muri Lagoon is located on the eastern side of the island, as shown in the right-hand part of that slide there. And it has 4 individual little motu or islands located on the reef platform. So that's what Muri often looks like. That's actually a photo from one of our field trips. It's not from a postcard, believe it or not. And yes, I would much rather be there than even on the south coast of New South Wales, as beautiful as it is, but not with the pandemic. So it often looks like that, but sometimes it can look like that as well. And that's actually a photo from, I think, February earlier this year, taken by my friend Lara Ainley, who works in the Ministry of Marine Resources over there. It has a lot of problems to do with water quality in the lagoon. And it's a result of a range of stressors, but mostly excess nutrients from both wastewater and also from agriculture in the catchment. So it's got a number of challenges, and I guess these challenges were the main instigator for the huge overall project that we were a part of, where we've done most of this work. Our investigations were focused on the flushing and hydrodynamics of the lagoon, so those physical processes, but there were other consultants and other universities looking at the groundwater movements and at nutrients coming off the catchment through the groundwater systems into the lagoon in parallel with our work. I'm only going to focus on the hydrodynamics today. So Rarotonga, I'll just give a bit of background about the island and the coastline. Rarotonga sits somewhere between a fringing reef and a barrier reef island in terms of its age and its progression. So it does have a separate lagoon. It does have a separate fringing reef detached from the mainland, but it is shallow. Different parts of the island vary between fringing reef and barrier reef classification, really. What that means is it's essentially a needle in the middle of the ocean. So they're the major contours coming up to the island, and you can see even the 500-meter contour is really close to shore. It's a really steep drop off once you get out over the reef. And that is significant for a number of reasons in the hydrodynamics of the lagoon itself. The prevailing wave energy and wind is onshore from the south and the southeast for most of the year. Again, this is significant for the hydrodynamics of the lagoon and the driving processes. So for the best part of the year, we have, it's getting most of the dominant wave energy along the fringing reef there. That's just a close-up of the lagoon itself. It's a couple of kilometres long. For the most part, it's varying between maybe 1/2 and 2 metres deep in different places throughout the lagoon. One of the locations that you'll hear me talk to about is the Arvina Passage, which is the deep natural passage at the northern end of the lagoon. And I'll make reference to that a few times throughout the talk. So we were basically engaged to provide a contemporary snapshot of what the hydrodynamics of the lagoon are doing. And it's not straightforward. I looked at, when we were planning out our investigations, I looked at previous studies that had been done at Muri, and there was a couple, and I've just shown some extracts from some of those previous studies here. But that gave us a bit of an idea of the kind of movement of water through the lagoon that we could be expecting, and we were able to use that information to kind of work out our arrangement of our monitoring program that we were going to take in our measurements there. So our study really that I'm going to present today has a few components. The first part was a bathymetric and topographic survey, and then we've also done a whole bunch of hydrodynamic monitoring. But one of the main concerns of the community was that the lagoon had been silting up over the years, and that had been restricting flushing and causing a lot of these problems to do with water quality. And that was quite a strong perception that we were challenged with understanding a little bit more about. So that is, I guess, one of the main drivers between updating a bathymetric survey, but also to help us understand the hydrodynamics. So the bathy survey was really quite complicated in this location. Because a lot of the lagoon is so shallow, we weren't able to get a boat through most of it. and it's so shallow that a lot of echo sounding instruments can't actually operate in it. You know, we're talking depths of 300 mil, that kind of thing, in a lot of places. So we had to really attack the hydro survey from a few different perspectives. One was to do a fixed wing UAV survey at low tide and capture everything above about minus 0.3 meters mean sea level, something like that. Where we could, we paddled the lagoon with a kayak that was fitted out with a single beam echo sounder. That's Chris Drummond on our purpose-built kayak there. In some spots, we were able to use a different version of the same sort of setup, a different type of echo sounder. But then in areas that were sort of intermediate, we had to wade a lot of the lagoon just with a pole and RTK GPS to get the depth. So it was a fairly lengthy process, and it sort of took us probably the best part of a week to get a good survey of the whole lagoon area. And that's kind of a mashup of the different data sets that we were able to obtain and the resulting bathy-topo model of the lagoon. I'm not going to go into a lot of detail about it, but what that really did allow us to do was to compare with some historical surveys of the lagoon and really look at locations that had changed in terms of gaining sediment over the time and other locations that had deepened. And it allowed us to dispel some myths and some hypotheses in the community about what had and hadn't changed in people's perceptions. So it was a really useful data set for that perspective. The hydrodynamic monitoring program that the baseline program was really undertaken over 4 months. We established 7 monitoring stations throughout the lagoon. They're shown there on the right. And the locations were selected on the basis of that historical information and how we thought the lagoon sort of operated. At those monitoring stations, they were equipped with a range of instrumentation, but we were basically measuring water levels, currents, waves on some of them, and water temperature. We had a separate mission to do current profiling in different parts of the lagoon, and we also released drogues at certain points to help us understand what was going on. These are just some pictures of our different monitoring stations in the lagoon. So currents were measured with a Marot tilt drag current meter. We used a range of different pressure-based water level loggers, and we used RVR duos for waves. So yeah, quite nice monitoring stations, a little bit different depending on the location. The bottom right photo there shows what we called Station G, which is right out on the Reef platform. At times that station's completely dry. That actually had about 200 kilos of weight to keep it there from when the swell was coming over it. So all the stations were sort of adjusted depending on their conditions. And we had different data sets coming out of the different stations. So most of them had water level, current speed and direction and water temperature, with the exception of that Station G. Station B and G had waves as well. And some of those data sets were being processed so we could get infragravity wave data, as well as wind wave data, different things like that. So we'll run through what some of the data sets look like. The first thing we're going to do is look at water levels in the lagoon and some of the things we learned from that. The main tide gauge for Rarotonga is actually located on the north coast, and I've shown it there. It's called Avatu Harbour, relative to where we're looking at Avana Harbour down at the right-hand side of that picture, at what we label monitoring station F. So what I've done here is just plot an extract of some of our water level data that came from that monitoring station F, where that blue dot is at the north of our lagoon. So that's nearest to the deep passage and the connectivity with the ocean. That is the solid blue line, and then the dashed blue line in this plot is the main tide gauge data. So the I guess if you like open ocean tide data. And what we can basically see, there was a previous idea that the tides at this part of the coast were lagged from the main ocean and from the north coast. And what we were able to see was that just wasn't true. There was the tides were completely in phase for that part of the lagoon. and fairly similar in elevation as well, at least for the bottom part of the tide. What was quite different though was when we started looking further into the lagoon, and I've plotted data here from our monitoring station B, which is that light blue dot, and the light blue line in the graph. And what was really apparent straight away was that the tides were super elevated within the lagoon. They were pumped up by different amounts at different times, which is quite interesting to see. The amount that it was super elevated varied. Sometimes it was only about 100 millimeters. Sometimes it was up to 400 millimeters. It just varied throughout time in the data set what that actually looked like. At low tide, it was typically higher. The tides in the main body of the lagoon were nearly always sustained at least about 300 millimeters above the open ocean. But when we look through time at the water level record in that main lagoon basin, what you can see is there's a really strong tidal signal, but the actual position of that signal is all over the place, up and down all over the place. And when we looked into it a little bit more, if we started averaging out across tides, and then we compared that to wave height on the fringing reef, what we found, of course, is that the water levels in the lagoon are really closely correlated with wave heights on the fringing reef. And there's a really strong link between that wave energy and between the amount that the lagoon water levels are super elevated. So it's quite interesting phenomenon. And when we went back and looked, this is not something new. This is something that other people have reported on over time. I've just shown some pictures here from some work that Dave Callaghan and others have published back in 2006 for one of the northern atolls of the Cook Islands. And they found much the same thing within the lagoon of the atoll, where water levels within the lagoon were super elevated above the open ocean, and that process being driven by wave energy on the fringing reef. If we look at we started looking at things in a lot more detail with our tide data to try and understand what was going on hydrodynamically in the lagoon, and I'll just talk about some of those nuances now. If we look at the tide range within the lagoon, what we can see is different areas, the tide range is constrained to a different degree. So if we look at the open ocean with a spring tide range of about 0.85 of a metre, that gets down to 0.55, where the pink dot there is within the lagoon. So quite a bit of restriction on the tidal range. And it's the same sort of restriction at neap tides as well, just shown there. But it varies in different spots within the lagoon. When we looked at the phasing of the tides, what we found was that at high tide, the peak occurs simultaneously in the open ocean to within the lagoon. But when we look at the low tide troughs, there's actually a lag, and it's it varies in the lagoon, but it's somewhere between 15 and 25 minutes at low tide. And that has some really important implications, and we can infer some really important things about that I'll go on and talk about in a minute. But probably the biggest difference that we noticed was that at high tide, what we saw was there was a gradient south to north in water levels. So at high tide, if you like here, the blue dot and the blue level was always higher, draining down, getting lower to the pink dot, and lower again to the black dot there, which is closest to the open ocean tide signal. At low tide, you don't have that feature. At low tide, there's no gradient in the water surface throughout the lagoon. The pink dot and the blue dot, or the pink line and the blue line, are basically the same level. Let's skip through that. And the other feature that we noticed was that the drainage of the lagoon, or the dropping of the tide in the lagoon, was significantly retarded once it got to a level of about 0.1 meters mean sea level. You can see that the curve starts to flatten off there. So all these little nuances are quite significant in understanding the hydrodynamics. And when we started plotting up the data as, if you like, a long section through the lagoon, which I've shown in the top of this slide here, what we actually started to find is that at high tide, you have that really pronounced hydraulic gradient running south to north through the lagoon. And then at low tide, there's no gradient at all. And likewise with the tide range varying throughout the lagoon, with the tides being mostly constrained about the middle part of the lagoon system there around monitoring station E. Now, so it's quite interesting to look through and consider the water levels and what some of this might mean in terms of the hydrodynamics. But what it sort of showed us was that everywhere from, say, monitoring station F and then out towards the ocean was pretty much getting open ocean tides, whereas the rest of the lagoon is quite separate and hydrodynamically different from the open ocean in terms of water levels. There's a lot more influence of waves there and a lot more influence of the bathy of the lagoon as well. Putting this together now with some data from currents, again, looking at the different monitoring stations where we were measuring currents, we looked at 1 minute current speed and direction at 6 of the stations and measured continuously across the 4-month period. I'm going to present data to you in current rows format. So this is just illustrating how we do that. So basically a current speed is the distance out from the center of the current rows, and then the direction the current is moving towards is shown as a compass direction, like that plot there. So if you like a 0.25 meters per second current to the north, shown in that figure there on the right, correlates to that dot on the graph on the current rows to the left. Over the course of 4 months, when we put all the dots in there, you get a scatter plot like that, which shows that at station A, it was sort of more often than not moving towards the north, but sometimes back towards the south. But what was quite interesting was when we started to actually plot all the current speeds relative to the water level in the lagoon at the time they were measured. And that's what's represented by the color of the dots in this current rows plot here. So red dots represent a higher lagoon water level and blue dots represent a lower lagoon water level. And what became very clear was that current speeds were very closely related to the water level in the lagoon, or the depth in the lagoon. Currents much faster at higher tide and or higher lagoon water level, and currents much slower at low lagoon water levels. As we move throughout the lagoon, looking at the different fingerprints of current patterns at each of the lagoon stations, we found a similar trend with faster currents at high tide and slower currents at low tide. You know, as you know, when we started looking at the directions of all the stations that supported the earlier information from the earlier studies, with currents tending to move from the south to the north, and then in between some of the islands moving from offshore to onshore, coming into this main lagoon channel. So it's just the current roses through the different locations, and currents finally moving northward and out through the passage at the northern end of the system. If we just look at, I'm going to plot data from 2 stations, the central station, monitoring station C there. We have on this plot here current speed on the x-axis versus lagoon water level on the y-axis. And what we started to see is that really clear trend between the higher the lagoon water level is, the faster the currents are driving through. And the same thing at the northern end of the lagoon, where the currents are moving further through the system before they go back to sea. Current speed is very closely linked with lagoon water level. Not too surprisingly then, if we looked at the current speed here, shown here is the thin blue line, and then average that across tide cycles, which is the thicker blue line, we can see that the tidally average current speed is closely correlated with wave height on the fringing reef as well. So same thing, water levels in the lagoon and current speeds really closely correlated to the wave energy along that fringing reef. So what this started to tell us in terms of going back to the original issues around water quality in the lagoon, what we're sort of seeing is that the flushing of the whole flushing of the lagoon is really closely linked to wave energy as the main driving parameter for this site and within the lagoon. Tides play a role in modulating the current speeds and the flushing, but the actual magnitude of currents and the actual flushing in the lagoon is mostly dependent on the amount of wave energy. When you have no wave energy and you still have tides, you don't get flushing. So it's not a tidally driven system. It's completely driven by the waves and the wave energy. What we started to see, which was quite interesting, and I've shown it here in this plot, going back and piecing this information together around water levels and currents and all the bits and pieces. If you recall, we talked about the water levels generally being more elevated in the main lagoon basin at high tide, more elevated there, and then draining down with this south to north gradient. And then at low tide, there was almost no gradient on water levels at all. Now that correlated really well with the same information about current speeds. Yeah. So what we were seeing was that at high tide, when the lagoon water level is higher, you have a bigger hydraulic gradient, faster currents moving through the system. At low tide, when you have no gradient in water levels through the system, you don't have anything driving those currents through. Everything stops at low tide within the lagoon. And what became kind of interesting for us was to understand a little bit about the interaction between the topography or the bathymetry of the lagoon and why that was happening. And what we actually found was that whole process of the lagoon not having drainage at low tide was linked largely with this section of the lagoon here in sort of the middle area, where there's really shallow ridge across the lagoon. And that so happens to be at the exact same elevation where water level stopped draining. Water stopped draining when we looked at those tide plots. So way back at the start, I said that once it got to about 0.1 meter mean sea level, the water level in the lagoon, it stopped draining. At that point, this ridge was becoming dry. And so this feature really holds back the water in the lagoon once you get to that point in the tide cycle. That was something that hadn't really been mapped out in the previous studies. So it's really piecing together the information about the currents and the water levels, but also how all this starts to interact with the bathy of the lagoon. That's just another photo showing that ridge across the lagoon, shallow there. It's just submerged at that point in time. As I said, we did do some current profiling in this particular, for a particular tide cycle in the lagoon. We looked at a complete spring tide cycle, and we monitored currents, quantified currents across most of the different parts of the lagoon across about a 12-hour period. Those current profiling locations are shown on the right-hand side there. Some of that was done with a weighting with a current meter, and some of it was done with an acoustic current meter on the kayak. These plots basically just show the currents exiting the lagoon down at the northern end, going back to the ocean, getting flow rates of up to around 50 cubic meters a second discharging from the lagoon back to the ocean, and that's at high tide. Again, the currents moving through the system closely following up, closely linked with water level in the lagoon in that tide cycle. So the deeper the water in the lagoon, the faster currents are moving through, and the more the lagoon's flushing. These figures just kind of showed the difference in flow rates between low tide on the left-hand side and high tide on the right-hand side, and how that split of currents are in different sections of the lagoon before they all come together and flow out at the northern end. So different percentages moving through the lagoon in different areas. So in terms of lagoon flushing, what we were able to kind of tease out was that about half the volume of the lagoon, this is where the bathymetry survey was really helpful, about half the volume of the lagoon is intertidal. And so half the volume of water is exchanged just through the rise and fall of the tide every tide cycle. If we look at the blue section down at the north, which is a deeper part of the lagoon, because that's the spot where all the water from the lagoon discharges, in that area, you have about 10 times of the volume within that part of the lagoon is being exchanged every tide cycle. So it's really well flushed in that area. Within the pink area, the intermediate sort of reef and channel zone, a lot of that's intertidal. So again, it's almost dry at low tide, covered by water at high tide, and it's really well flushed because of that process, just that exchange of water levels. In the main lagoon basin, what we found during the monitoring period was that most areas are probably getting flushed about every 1 to 2 tide cycles, something along those lines. There were spots where the flows were quite low, But that was to do with the shape of the lagoon. And so they had lower, quite a bit lower flushing. So there's some dead zones with poor circulation, but most of it was flushed quite well. And that was quite an important finding to take back to the community and discuss in terms of water quality issues and people's concerns about it silting up. We went on, so that was all field-based work. We did go on to do some further work looking at numerical modelling of the lagoon and the hydrodynamic processes and this whole wave setup driving flows and flushing through the lagoon. The graph at the top left there just kind of shows the relationship between significant wave height and that super elevation or pumping of the lagoon water level that drives the whole process. But one of the things that started to become apparent for us was that given the system is so closely linked, or the hydrodynamics are so closely linked with the wave energy on the reef, is that it's going to be very seasonal because the wave energy was seasonal. And this goes back to some of those wave energy plots I showed back at the start of the talk. What we actually find is that in winter, you get a lot of southerly wave energy, and that is what drives a lot of the flushing of the lagoon. But in summer, you get a lot of easterly and even northeasterly wave energy on the reef here. And so that takes away that south to north gradient in wave setup process. And so it actually changes the way the lagoon flushes. And that's something we've been looking at more closely over the last sort of year or so. I'm not going to present all the details here, but the idea is that with the southerly wave climate, you end up with a bigger gradient south to north in wave setup through the lagoon, and really drives those flows out through the deep passage at the north. Versus if you have easterly and northeasterly wave direction, the flow patterns in the lagoon become a lot more disturbed and you have a lot more of these dead zones and the whole thing doesn't flush as well. And that's a seasonal process. So one of the questions we were tasked with answering was that the community really felt that some parts of the community really felt that dredging the passage at the north was the solution to increase flushing of the whole system. And that sedimentation of this passage over time was responsible for blocking the flushing of the whole lagoon. And by having a much better understanding of the whole system and what the drivers are for flows moving through and being linked with waves and all these things, and how the water levels in the lagoon operate relative to the bathymetry, we were able to answer some of those questions about to dredge or not to dredge in that northern passage. And if we go back and have a look at some of our cross-sectional plots and our water levels relative to the bathy, what we're able to see is that water drains through the system quite well at high tide. As the tide starts to fall, you get two things going on. You lose that hydraulic gradient that drives water from south to north through the whole lagoon. And that happens because it starts to be held back by that shallow ridge in the center part of the lagoon. It's got nothing to do with the passage at the north of the lagoon. So even though the community was wanting to dredge that passage because they know that's where currents discharge from the lagoon, that's actually not the controlling feature. The controlling feature is a shallow area within one of the lagoon channels. So dredging further north, and that would have absolutely no impact at all on the lagoon flushing further south. And we were able to answer that quite definitively with the data. Something else that's quite interesting though, is that at about the same time that shallow ridge starts to really control and restrict flows through the lagoon, the outer fringing reef is becoming dry. They're almost the exact same elevation. And so once you get to that point, you don't really have a lot of exchange of water coming over that fringing reef anymore anyway. The waves aren't passing over there unless it's really high wave energy. So if we were to flatten that ridge out, while you might let more water out of the lagoon at that low tide point, you're not going to have more water driving through, and you're not going to have that process of wave energy setting up water level in the lagoon because the waves are disconnected at that elevation. So all that's going to serve to do is drop the low tide water levels in the lagoon further. And that has a whole host of other problems for the lagoon, given that it's in equilibrium with salt marsh areas, corals, and all these other things that are sustained throughout the lagoon. If we lower that water level, you will change a lot of that ecology. You change the water temperature profile. You do all sorts of things. So again, all this data and understanding these interactions between waves, water levels, currents, and the underlying bathymetry started to allow us to answer some of these complex questions around whether or not we should be modifying sections of the lagoon or not to increase flushing, and if in fact flushing was a part of the problem at all, or if it's all driven by catchment nutrient loading and that kind of thing to the water quality issues in the lagoon. So I guess some of the key points that we took out of it, of doing this kind of work, given that it's so complicated and it's not a typical system where, you know, like with our estuaries where you have tides really driving the flows in and out of estuaries, this is something where tides play a role in modulating the system, but it's really driven by wave energy and wave setup processes. And to really understand how the hydrodynamics are working, you really have to understand from field data how the water levels are all sitting relative to each of those bathymetric features in the lagoon and how the whole system's fitting together. As I said, water levels are really closely correlated to wave conditions on the fringing reef, and so are currents, because it's the water levels setting up these hydraulic gradients, this wave setup process and a hydraulic gradient through the system that then drives that overall south to north flushing. So yeah, it's really this interaction between tides and the tide water level and the wave energy that dictates all the hydrodynamics of the system. Something that we learned from the numerical modeling was the effect of wave direction on wave setup and those hydraulic gradients and the flushing of the lagoon. And we've just started to look at that more now, the seasonal variation in that, but also the links with ENSO and wave energy on the reef. And that's actually the topic of a paper I'm going to present at Coasts and Ports later in the year. And there's some really interesting things to learn out of that as well, given that the whole system is closely linked with wave energy, and wave energy is quite a seasonal thing. Generally, the lagoon is quite well flushed overall, but there's periods, in particular during summer, when there's low wave energy and sections of the lagoon don't flush well at all. And it's these periods that are critical for water quality, algae outbreaks, all of these kind of things that are algal blooms, all these kind of things that are really causing the, being seen in the lagoon as the main impacts, in particular summer like the last summer that we've had now. So most of the time, there really is no need to increase flushing of the lagoon. Certainly during some periods, it probably could be improved a little bit, but overall, the problems that they're having with water quality there are associated with catchment inputs, not hydrodynamics of the system. And by doing this kind of work, we're able to tease all of that out and look at that in a bit more detail. Something else to think about. Back at the start, I said that this is the kind of site that keeps teaching you different things about coastal processes and about doing this kind of analysis and field data sets. And this is something that I've reflected on since doing this project that I thought I would share with you. It's quite interesting. This is an aerial photo of the lagoon from 2004. And there's some interesting little features in here that I'll just put some lines over the top of there that are traditional fish traps. They're mounds of rocks. You can see a close-up one there. It's the northern one that's shown up close there in the right-hand image. These are mounds of rocks that have been built over time by the traditional community in the area as a way of funneling fish, if you like, into one particular location to be captured within the lagoon. What's really interesting is to reflect on the positions of these fish traps now that we know how the hydrodynamics of the system work and we've mapped out where all the current flow paths are, and start to ask a few questions about why these fish traps are located where they are. They're not around the rest of the coast of the island. There's a couple, but mostly they're in this part of the lagoon. And you can start to see some things like they're all located within the main flow channel of the lagoon where the dominant flow paths are, which really makes sense. But if we look at the southernmost fish trap there, it's quite small. It's not taking the full width of the lagoon channel. The flows there are about 1 meter a second when they're really moving. So you probably wouldn't be able to build a structure like that from small rocks and constrain the flow. So they've only blocked or taken off flows from a part of the channel. The second one located there is where the lagoon is much, much broader and shallower, and the flows aren't as powerful, and it's captured most of the main channel flow path. We might ask ourselves why the second fish trap from the north is located where it is and being quite small. You would think that everything flowing past there at first glance would be captured by the fish traps further south. But in actual fact, when we start to look at the currents moving through that area, the flows on the right-hand part of that channel all come from the outside lagoon in that area. They're a completely separate source of flows moving through the lagoon. They're all coming from the outer fringing reef in between those two motu and running through where that small fish trap is. And so it sort of goes as you move your way north. So on reflection, while we've gone in and used a lot of technical methods and equipment to look at all the flows and the movement of water through this lagoon and come to some conclusions about it all, looking back at some of the traditional knowledge and how that's been used in the past to plan things like fish harvesting could really have taught us a lot of the same lessons and a lot of the same information about this particular site. So that's, I guess, for me, some little piece of information that I've learned to consider in a little bit more detail when I'm planning these kind of studies in these kind of locations, and to look at these kind of things and talk with some of the people with traditional knowledge about these systems, as well as our modern way of analysing them, which I thought was quite interesting. So I will leave it there and have some questions and some discussion, hopefully.